So today is the lecture 4. Basically, we are talking about the basic reactor physics concepts. We started with nuclear physics and nuclear cross sections, and now I had introduced basic reactor physics. This is a part 2 where we would be formulating the neutron balance equation. A recap of the last lecture, we were looking at the neutron cycle. What is the multiplication factor? Then I introduced the 4-factor formula. I also defined all the 4 factors, which is eta, epsilon, p, and f. And I had also mentioned that eta and epsilon are the properties of the material or the fuel, and f and p are the properties of the fuel in the medium. So it can be optimized so that you can get a K infinity with a proper moderating as a medium. I have also given you the distinction between the infinite and finite reactors. What is K infinity, which is basically the multiplication factor for infinite system, and K effective is the multiplication factor for the finite system, which involves a non-leakage probability. We also defined the non-leakage probability, and we also saw some of the neutron diffusion phenomena, and the law which is governing the neutron diffusion is a fixed law, and thereby we derived a expression for the neutron current density, and we said how it was proportional to the scalar flux. And we also saw about how the neutron on scattering with the heavy nucleus loses energy, and what is the energy lost in a single collision, and how the slowing down happens and what happens during the slowing down. I also defined 2 concepts. One is the lethargy, and then the average logarithmic energy decrement. So these 2 will be governing how a neutron loses energy with respect to the scattering collision or the elastic collision. And I also mentioned that lethargy is a better unit because we are dealing with energy scales which are ranging from MeV to almost electron volts. So we say a dimensionless quantity, which is lethargy, which is a logarithmic change in the energy of the neutron. Then I have introduced the concept of moderation. I have also told you that why a combination of natural uranium and light water cannot go critical, but whereas natural uranium and heavy water is a critical combination where we can get a K infinity more than 1. And therefore, some concepts of moderation I have told you. And I have also told you that while light water reactors, the fuel has to be spaced closer, and in heavy water reactors, the fuel is placed a little farther away. At the same time, we were discussing about the spectrum of neutrons. Neutrons are in thermal equilibrium with the moderator, so acquire the temperature of the medium, and thereby it follows the Maxwellian spectrum. And the maximum probability velocity of thermal neutrons also we had seen the expression for it. And we also saw that if the thermal neutron is of energy of 0.0253 electron volts, then its velocity would be 2200 meters per second. I also given you some distinction between homogeneous systems and heterogeneous systems. Homogeneous system is where the fuel and moderator are mixed homogeneously in a medium. And heterogeneous system is basically where you have distinct fuel rods present in a moderating medium or material. And I also gave you some of the design aspects with respect to slowing down power, with respect to number of collisions required to come down to thermal energies, and so on. So today, what we would be talking is, what are the basic components of a nuclear reactor? Then I would go on to explain the neutron balance equation. We will derive the neutron balance equation in a very simplistic terms. I would also tell you some properties which is concerning with respect to the neutron balance and the shape of the neutron flux in a reactor. I would give you the criticality conditions with respect to material and geometric buckling. We will derive some expression for a non-leakage probability. I will give you the concept of criticality, subcritical and supercritical reactors. and the flux profile in a bare reactor and a reflected reactor. I would also give you an emphasis on how the thermal diffusion length is defined, and also some concepts of the migration length, and some exposition to the reactor design and analysis. When we are talking about all these, we have to say what is a reactor power. So I will give you the definition of reactor power, how do we calculate it, and actually what is meant by the burn up of the fuel, because I have already told you that fuel is getting depleted, it is giving away energy. So in terms of the burning of the fuel, we have defined a quantity which is a fuel burner, and this is one of the important characteristics for the fuel utilization. I will briefly touch upon some time dependent behavior in order to you to appreciate that in a reactor, we don't always have a dynamic equilibrium. There could be some deviations from the steady state conditions. So let us first derive this neutron balance equation. So this neutron balance equation is basically, in general, in the multiplying medium, it can be written as the balance between the production mechanism and the loss mechanisms. You are able to see my cursor when I'm moving the cursor, right? Okay, the production mechanism consists of fissions, which is happening in the volume, and scattering into the volume. Scattering means a neutron which is of higher energy gets elastically scattered and comes down to thermal energies. So that also could be causing a fission. So they are the scattering source, we call it. So the production mechanism is basically due to the fission process and due to the slowing down process which is happening in the volume of interest. In our case, it is a reactor or a chain reacting volume. The loss would actually then be absorption in the volume, that is the neutrons I have already told you that is getting captured or non-fissile capture which is happening, and because that it is lost from the system. So the loss mechanisms consist of absorption, and because we are talking about finite system, there could be a leakage out of the volume. So the neutrons will go out of the volume, and so they contribute to the loss mechanisms. So in a nutshell, there should be a balance between the production and loss mechanisms. So let us first consider only one group of one energy neutrons. We call it monoenergetic neutrons. Let all the neutrons be of thermal energies. Then we can write the rate of change of neutron population, which is given by dN by dt, is nothing but the source in the system, which is S, which is basically coming from the fission source and the scattering source. And then there is an absorption in the system or capture in the system, and there is leakage. So S minus sigma A phi. Sigma A into phi is the reaction rate. This I have already impressed upon you. That is, this is the macroscopic absorption cross-section when multiplied by the scalar flux. This gives you the reaction rate, and this sigma A into phi is going to be the total loss or absorption in the volume. And the leakage can be written as just leakage right now. I will derive an expression for this shortly. So S minus sigma A minus leakage is going to be dN by dt. So the leakage can be derived in terms of the net current density across the surface in a volume. That is, the neutrons are leaking out from one volume to another volume in a reactor. So this you have understood, I suppose. That is, the rate of change of neutron density is a balance between the production mechanisms and the loss mechanisms. So first, let us talk about how to calculate the leakage. Let us consider a simple volume. I am just taking Cartesian coordinates for the ease of our understanding. And here you can see that this is X, Y, and Z. I have considered a small cubic volume. And I have also told you that this is the small volume dx, dy, dz. So we are trying to calculate the net neutrons which are leaking out in a direction perpendicular to the XY plane. So suppose you say that the number of neutrons entering this volume is Jz, and the number of neutrons which are coming out of this volume is J of Z plus dz. So the net rate of loss of neutrons from this volume element parallel to the xy plane is given by J of at calculated at z plus dz minus J calculated at z multiplied by the volume dx dy, which is nothing but dz djz by dz, or the net rate of loss of neutrons per unit volume will be nothing but your d dou jz by dz. That is the rate of change of neutron current density in the z direction. So this can be given by, this is in one direction, which is z direction. So the net rate of loss of neutrons in the whole volume will be from all the three components, that is jx, jy and jz, which is given by djz by dx, djy by dy and djz by dz. So this quantity is nothing but divergence of J. So this divergence of J will give me the net neutron leakage from the volume. So therefore, we can formulate the equation as S minus sigma A into phi minus divergence of J is equal to dN by dt, or rate of change of neutron density. We have already introduced you the fixed law of diffusion for you, where we have calculated what is the neutron current density. So the net rate of neutron flow in a given direction is proportional to the negative of the spatial gradient of the flux. So Jz is nothing but minus d into dou phi by dou z, where d is known as the diffusion coefficient. And if you substitute this in this equation, we get an expression for leakage. So I hope you have understood this. That is, we are trying to calculate the net leakage of the system, net leakage of neutrons from the system, which is nothing but governed by the fixed law, which says that always neutrons are going to flow from the high neutron density to the low neutron density, just like your gas molecules or any other thing. So thereby we say that from fixed law, J is nothing but minus d grad phi. So the fixed law of diffusion says J is nothing but minus d grad phi. And so therefore we substitute all this in this equation. So you can get the leakage term. I have just rearranged the terms so that the plus and minus come together. So the divergence of d grad phi. Here I have introduced a concept of R. Basically, spatial is going to be R. In general, when we are talking of the space coordinate, we represent it as R. So this is phi of R minus sigma A into phi of R plus S of R is nothing but dN of R by dt. So this is the rate of change of neutron population, which is given by your production term minus your absorption term and your leakage term. There is already a negative sign here, so that is why it comes negative of negative becomes positive. So this is the leakage term. So leakage is nothing but divergence of your current density, and current density is nothing but d into grad phi. Now for a homogeneous system, we say that d is independent of space, because we just say that when we derived fixed law, we said that it is a one medium is having one property, so the d is same and it's not is invariant. And so we can say that for most applications, we consider d to be independent of R or space. So from this, we have derived the neutron equation, balance equation, which is nothing but d del square phi minus sigma A phi plus S is equal to dN by dt. Now in a steady state, we know that dN by dt is going to be 0, or in a critical reactor where the production and loss mechanisms is always equal and your reactor is in dynamic equilibrium, your net change of increase of neutrons is not happening. So in such conditions, your dN by dt can be put to 0. So if I put dN by dt to 0, then for a steady state, the neutron balance equation becomes d del square phi minus sigma A phi plus S of R is equal to 0. Now I divide the whole equation by sigma A. So here del square phi minus 1 by L square. I do all these mathematics so that you get some simpler form of a mathematical form of this equation, which can be solved. So here when I am saying sigma A by D, this quantity I define as L square, which is basically, I'll come to a little later, it will be called as the diffusion length. So I define L square is equal to D by sigma A. So this steady state equation becomes del square phi minus 1 by L square phi plus 1 by D of S is equal to 0. I hope this is quite comprehensible. This is not very difficult. We started with a simple definition of production and loss, what is happening in a chain reacting system or a volume. Then we try to derive the different components of the productions and the loss. And finally, we have ended up in a equations. Now, I had told you that I will explain a little more about this L. This, when we have considered all the neutrons to be thermal. So they are diffusing in the medium as thermal neutrons, and they are moving and they are colliding with the moderator atoms, and they are either losing energy or gaining energy, but the net energy is going to be almost thermal. We have defined a quantity L, which is nothing but root of D by sigma, average D by average sigma, where D average and D sigma is averaged over the thermal neutron energies, almost 0 to 1 eV, where I have explained to you about the Maxwellian spectrum. So if I take the Maxwellian spectrum and average the cross section sigma A and D over that, then your L is nothing but root of D by sigma A. This, you have to understand the physical concept of this diffusion length. This neutron is diffusing in a medium. So it diffuses over these distances until it is going to get captured by a nucleus. So diffusion length can be understood as the length or the distance over which a thermal neutron travels before it is getting absorbed. So the distance over which the thermal neutron travels before it is getting absorbed. So this, if you say, it is dependent upon the material properties or properties of the medium, which is nothing but your D and sigma A here. So in simple terms, we can understand L to be dependent on the material properties, which is the diffusion coefficient. Again, this diffusion coefficient is in the order of centimeter, and sigma A is of the order of centimeter inverse. So this L will also be centimeter or meter, have units of length. Now I have also tried to give you some diffusion properties of moderators for thermal neutrons, so that you will have a better understanding of what we are talking about. See, I have given here 4 major important moderating materials, which is light water, heavy water, beryllium, and graphite. And these are the densities in kg per meter cubed or gram per centimeter cube. This is L, which is the diffusion length, which is in meters, and this is D, which is the diffusion coefficient, which is in millimeters. So you can see that light water, I had already impressed upon you yesterday that L is of the order of 2.7 centimeters. That's what I have told here. And heavy water, it's about 1 meter. So heavy water lattices are going to be spaced far apart. Or heavy water reactors are going to be huge in dimension, and light water reactors would be very little smaller in dimensions. And the diffusion coefficient for heavy water is about 8.5, beryllium is 5.4, and so on. So these are the different properties of, you can easily see that when absorption cross section is very less, L is going to be very high. So that means heavy water has the least absorption, and that is why its L is, or the diffusion length is very high. So the thermal neutron will have to travel almost around 1 meter in a heavy water lattice to cause further absorptions in further nuclei. So this is what I wanted to make you understand, that the length or the diffusion length will decide how to design the reactors, whether it's a light water system or a heavy water system, and what type of fuel we have to use. So now let us talk about a little more about the critical equation, because finally we need to find out the how the flux varies with respect to space. Because the solution of this equation is going to be phi of r. Phi of r is nothing but the spatial dependence of the flux with respect to the dimensions of the reactor. So in a critical reactor, the steady state is maintained without external source. So the source, let us say, this source is basically going to be 0. You are going to only have your fission source. So the S will actually be so I have already told you that K infinity is a multiplication factor. Sigma F, if so, K infinity neutrons are being produced at 1 generation. So this many neutrons can get absorbed as thermal neutrons in a reactor. So in a chain reacting system volume, which is having properties of sigma A. So K infinity into sigma A into phi can be called as a source of neutrons, which is an internal source due to fissions. So this many neutrons are going to be produced. So this S of R is nothing but K infinity sigma A into phi. So I substitute this S in this equation and rearrange the terms. So here you can see that del square phi plus K infinity minus 1 into sigma A by D into phi is equal to 0. So basically I'm doing this to see that we have a simple wave equation kind of a formalism. So this can be written as del square phi plus this whole quantity K infinity minus 1 by D into sigma A, I call it Bm square. So this del square phi plus Bm square phi is equal to 0. So this, our equation, our neutron balance equation has become so simple. So since we are talking about the neutrons which are moving in a chain reacting system or in a volume of interest or region of interest for us, we have used those material properties and it's a multiplying medium, and try to derive a equation which is a governing equation for this neutron flux or neutrons which are being diffusing in the medium. So this K infinity minus 1 by D into sigma A, I have written as this to be a quantity called Bm square. So this is the source which I have already told you, that is nothing but K infinity into sigma A into phi, which is nothing but the fission source. K infinity already I have told you is an infinite multiplication factor, which is a rate of neutron productions to the rate of neutron absorption. It is a ratio of this rate of neutrons which are produced to the rate of neutrons which are lost. And this, if I have so many neutrons after one generation, which can cause fission, then my fission source, which we call as a fission source, would be nothing but your K infinity into sigma A into phi. Now this quantity which I have already told you, that is this again sigma A by D can be written as L square. So here I say that Bm square is nothing but K infinity minus 1 by L square. This is the property of the material, or it is called as a material buckling. This equation is considered can be considered like a wave equation, which is giving you the curvature of the flux. The flux, you are solving for the flux, so it's a curvature of the flux. So this Bm square can be called as a buckling. And because it is dependent upon the material properties, it is called as a material buckling. So if I write the K infinity equation, if I rearrange this same equation and write it, I can write it as K infinity by 1 plus L square B square is equal to 1, which is nothing but K infinity into, I was telling you we will derive a expression for non-leakage probability. So this is called as a condition of criticality, where K infinity by 1 plus L square Bm square should be equal to 1. So this fact, quantity 1 by 1 plus L square Bm square can be called as non-leakage probability. So this can be, because yesterday we saw that K effective is nothing but for a operating reactor in a steady state conditions, when production mechanism is balanced with the loss mechanisms, your multiplication factor should be 1. So we said that K effective should be 1 is the condition, and that is a condition for criticality, which means this, which is a steady state has reached, and that is given by K infinity into PNL. So this is the expression for the non-leakage probability for neutrons for specific energy. Now we are also talking about a finite reactor, which is, let us say, a slab or a square or a cylindrical or a sphere or so on. So when I derive this wave equation here, when I derive this neutron balance equation, I have told you that it is we have derived it as for no external source. We said that it is del square phi plus B square phi is equal to 0. So that is nothing but if I take that a geometrical representation for the flux or the finite reactor, if I take, so you have this B square is nothing but the BG square, which is called as a geometrical buckling of the system. So the condition for criticality is that this material buckling should be equal to the geometric buckling. That is, how much of fuel should I put into the reactor? That would depend upon this material properties and size of the reactor. So, so if Bm square is equal to Bg square, then we have a critical system. For example, let us consider a small sphere. If you consider a sphere, this buckling B square is given by pi by r the whole square. So your material property Bm square should be equal to Bg square. Now we can calculate the critical radius, what is required in terms of the material properties. In simplistic terms, you can do this exercise for some typical numbers. Then you will see that what will be the typical critical radius of a sphere. So this k infinity minus 1 by L square should be equal to pi by r the whole square. That is, Bm square should be equal to Bm square. Bg square, material buckling should be equal to the geometric buckling. The geometric buckling is given by pi by r the whole square. So here you can see that the critical radius is nothing but pi into L divided by root of k infinity minus 1. So if I have a k infinity of, let us say, 1.145, which I showed you in the other expression, you can calculate what is the, you know this, and L is already for heavy water system. Let us say you take 1 meter, then you can calculate the critical radius. This is a simple formula which gives you the critical radius for a spherical system. But similarly, you can have a cylindrical system or a slab system and so on. I hope you have understood what is the definition of material buckling and how we have derived material buckling in terms of the material properties. And we have also said that from the expression of the flux, which is nothing but from expression for the diffusion equation or neutron balance equation, we say that del square phi plus Bm square is equal to 0. And we also said that this would be actually depending upon the geometry of the system. So we have something called as a geometric, it is a curvature of the flux. This equation gives you the curvature of the flux. And so therefore, we can say that it is a geometrical buckling. And the condition for criticality is basically when you have Bm square is equal to Bg square, you have a critical system. So again, I would like to explain a little more about this geometrical buckling and the curvature of the flux. Let us consider a simple system where we have a core and a reflector region. Here I am trying to plot the flux profile. If I plot this equation, it will become something like this. So the red one is the flux when there is no reflector, let us say, and the blue one is that when there is a reflector. You know that reflector, it can give you more thermal neutrons. So there will be a slightly peak of thermal neutrons here, and then it would reduce. And whereas similarly, this is a simple cylindrical reactor which I have taken. And the equation we already know is del square phi plus Bm square is equal to 0. So the general profile follows the Bessel function, which is, you can see its similarity between the mathematics, which is del square phi plus k square phi is equal to 0, and k square can be considered as the curvature of the flux. And in this respect, it is also called as a geometrical buckling and is represented by Bg square. So when Bg square is equal to Bm square, we have a critical condition, and when Bg square is greater than Bm square, we have subcritical, and when that is the material is less than what is required for criticality, so it is a subcritical system. Subcritical system means your neutron population will keep on dying down. So K will keep on reducing below 1, and finally it will decrease. If Bg square is less than Bm square, then we have a supercritical system. So this is again a situation which is called as a runaway situation, where the neutron population will keep on increasing with time, where K is equal to more than 1. So at every generation, you are getting more and more neutrons, and thereby your condition of criticality is not maintained. So it becomes a supercritical system. And if it is very large supercritical, it would lead to runaway situation. So this is the concept of criticality, subcriticality, and supercriticality. With respect to K, we can also say that K is considered as an excess multiplication factor. I had told you, it is an excess multiplication. K is a multiplication factor. So K minus 1 can be considered as an excess multiplication factor. And we already know that condition of criticality is K is equal to 1. So I am introducing one term called a quantity called reactivity, which is very important in reactor physics and in the reactor core, which we are going to generally talk about tomorrow and so on. Here, the fractional departure from K is equal to 1 is called as reactivity. So we just define a term rho, which is nothing but K minus 1 by K, which is a fractional departure from criticality. So if this rho in an operating reactor should always be equal to 1, because I told you it's a dynamic equilibrium, K should be maintained 1, so rho should be 0, rho should be 0. There should not be net reactivity in the core. So that means your chain reacting system is balanced and your production and loss mechanisms are balanced. Yesterday we saw the neutron lifetime or neutron cycle. There are so many processes which is happening. Neutrons are produced, neutrons are getting captured, neutrons are getting transmuted, and neutrons are getting absorbed as fast neutrons and produce more neutrons. There are so many dynamic processes which are happening in the reactor. And this reactor is a dynamic equilibrium of all these processes. And we try to derive the equation which is governing this dynamic equilibrium, which is a neutron balance equation. And then we have seen what is the condition of criticality. So when production and losses are balanced in a critical reactor, there is no net change of neutron density, or the net change of neutron density is 0. So if K is equal to 1, it is a condition for criticality. If K is less than 1, I already just now mentioned to you that the neutron population will keep on dying down. And so therefore, it is called subcritical. The chain reaction dies down and the neutron density decreases with time. And similarly, if K is equal to 1, greater than 1, it is called a supercritical, where the neutron population will increase with respect to time. So here, just take the that I have introduced a concept of reactivity, which is the fractional departure from criticality, and I have introduced to you what is critical, subcritical, and supercritical system, both with respect to K and with respect to the material and geometric buckling. I think so far you have understood. Now a little more about buckling and non-leakage probability. See, this non-leakage probability can also be written as K by K infinity. That is, we have already seen that K is for the finite system and K infinity is for the infinite system. So this ratio is nothing but your non-leakage probability. So it can be considered as rate of neutrons absorbed divided by rate of neutrons absorbed plus the leakage rate. We have already derived expressions for all these things. So we can write it as sigma A into phi divided by sigma A into phi minus d del square phi. Now here we have this neutron balance equation, which is del square phi plus bg square phi is equal to 0. So you substitute for this. This can also be written as minus d del square phi. You substitute for bg square and you substitute for del square phi here. So you can nothing but minus d del square phi is nothing but your db square phi. So this quantity is nothing but, and multiply by d on both sides. I take it to the right hand side and multiply by d on both sides, and there I can get what is the quantity d del square phi equal to, which is nothing but in terms of the geometric buckling, it is equal to db square. So the expression for non-leakage probability can be written as sigma A phi divided by sigma A plus db square phi dbg square phi, or it can be written as 1 by 1 plus d by sigma A into bg square, or this is nothing but your non-leakage probability. PNL is equal to 1 by 1 plus L square bg square. This d by sigma A is nothing but L square. So your non-leakage probability we have derived in terms of the material properties for one group energy of neutrons, one energy neutron. Because so far we are always saying that it is monoenergetic neutrons, all neutrons are of single energy and so on. So now we have derived an expression for your non-leakage probability. This immediately you can say that bg square is a geometric buckling depending upon the dimensions of the system. If the dimension of the system is large, your non-leakage probability is going to be less, which means that if I have a larger reactor, the leakage is going to be reduced. But then I cannot have a very large reactor. So we optimize the reactor dimensions so that we get a proper K. So this non-leakage probability is a function, can be defined as 1 by 1 plus L square Bg square. L is a material property, B is a geometrical property. Okay. So, now, so far we were talking about only one energy neutrons. But actually in reality, in a reactor, you would have so many neutrons of so many different energies, and we have to treat the energy of the neutrons also. But in a thermal reactor system, I have already told you that when you have neutrons are colliding with hydrogen, most of its energy is lost in a single collision. So generally we can safely assume that in a thermal reactor, we have only two major neutron energy groups, where you have a fast energy group and a thermal energy group of neutrons. I am grouping the neutrons. So far, we have considered the spatial variation of neutrons. We got the Bessel function for the spatial variation of neutrons. Now we also have to talk about the energy dependence of the neutrons. So let us say neutrons are born at around 20 MeV of energy, and it comes down to the thermal energies, which is 0.0253 electron volts. At the energy domain, I divide into two major regions. This is a fast energy region, which a thermal cutoff at around 0.625 electron volts. This is a fast region, and this is the thermal region. This thermal region is governed by the L square, which is the thermal diffusion length. Now this fast energy, we'll come to this fast energy region. Now we have something called, yesterday I was talking to you about the slowing down principles. The neutron is continuously losing energy on collision. So this is how the neutron is going to lose energy in a, let's say, absorber of large mass, and in hydrogen it will lose energy faster. So you can see this. So this is called as a continuous slowing down model. So if you have a medium of nuclei of uranium-235 or U-238 or natural uranium and so on, and you have neutrons, the neutrons are continuously going to lose energy because of successive collisions. So this whole thing, when I'm trying to formulate the equation, we have characterized the slowing down energy range by a factor called as tau. This tau is nothing but it is the age of the neutron. That is how the neutron is going to get born as a fast neutron and come down to thermal energies. So it is defined as an age of the neutron, and is defined, okay, I'm not writing that expression here, but basically it is has the dimensions of centimeters again. So age should not be confused as age like what we know. It is the age, that is how the neutron is going to be captured before it is getting lost. As the neutrons are slowed down, it may get lost because of captures, which should not happen. It should come down to thermal energies. Only then it will cause fissions as thermal fissions. So what is the effective distance the neutron will travel as a fast neutron before it gets to thermal energies? So this is characterized by a quantity called tau. And then finally, if we have this two group energy formalism for the neutrons, then we can write the criticality condition as k infinity by 1 plus L square plus tau into Bm square. L square and tau. Here L square stands for the thermal neutrons and tau stands for the fast neutrons. So this quantity L square plus tau is called as the migration area, or migration length is root of L square plus tau. The migration length, this is what I told you. There are two important concepts: diffusion length and migration length. Diffusion length is the distance traveled by a thermal neutron before being absorbed. This I have impressed upon you in so many slides. Migration length is the neutron is born as a fast neutron and finally it will get captured as a thermal neutron. So it is a distance over which the neutron which is born as a fast neutron will get captured as a thermal neutron. So this I have tried to explain schematically with two different energy regions, where it is spanning the entire energy region of the neutrons which are in a reactor. And generally, two group formalism is sufficient for a thermal type of reactors. And so here we say that you have a slowing down age or slowing down, which is the Fermi age, which is called, or sometimes it's also called a slowing down age. So this is defined by tau, and this sometimes it's called as a slowing down length, which is called as LS square. So tau is nothing but LT. This is L thermal square, and this is LS square. In same parlance as the thermal thing, you can derive the fast or the slowing down length in the fast regions, and thereby it is also called as LS square or tau. So this is a continuous slowing down model which is being applied, and here you get the migration length or the migration area. In the next slide, I think I have given some okay, maybe it is there somewhere else. I am not very sure. I can give you the difference between M and L, but maybe if I am getting the slide, I'll give you. But before we go further, we need to know certain other things for the nuclear reactor. One basic thing is, what is the power? What is the fission power? You say, I have also impressed upon you that the reaction rate is what is giving you the power. So the fission reaction rate is nothing but sigma F into phi. So many fissions per meter cube is what is happening in the volume. So considering the average, it is shifted here, but considering the average of sigma F and phi, we can write that P thermal is nothing but sigma F into phi into the volume. You have to multiply it by the volume because this is all per unit volume per meter cube. And then we have already told you in my first lecture that each fission, one watt, to produce 1 watt of fission, to produce 1 watt, you require 3.1 into 10 to the power of 10 fissions. This can be calculated from the 32 picojoules, which I have told you. So P thermal is nothing but V into sigma F into phi, the reaction rate due to the fission reactions. This is the averaged over the energies, and this is the average flux. So you can directly see that if the flux is changing, the power could change. So I keep on increasing the flux, then we can change the power. So the power level can be changed by changing the flux level. See, the expression for P in terms of the reaction rate or the fission reaction rate is V into sigma F into phi. Now there is one more quantity which needs to be introduced, which is burn up. Burn up is basically the amount of fuel which has got burnt. It is a characteristic of the fuel. It's basically the amount of depletion of the fuel or the energy produced by the fuel. The amount of energy extracted per unit mass of the nuclear fuel is called as burn up. Now, I had again told you in my first lecture, you have seen the presentations. I hope you have downloaded it from the Anuvidya site, I suppose. So you can see that the energy from one fission is 32 picojoules. So the complete fission of 1 kg of uranium-235 will give you 80 terajoules. That is 80 into 10 to the power of 12. You do the mathematics and divided by the seconds, then you will be getting 1 kg of uranium gives you, this is per day, you have 24 hours. You can calculate 925 megawatt day. This is in terajoules. You can make it into megawatts. Then you divide by you can convert the seconds into days, you will get megawatt day. So you see that to produce this much of energy is in terms of megawatt into day. Kilowatt hour, you must be knowing that is a unit of electricity. Similarly, megawatt day is a unit of burn up here. So you can say that 1 kg of uranium-235 gives you 925 megawatt day. Or in other words, 1.05 kg of uranium-235 gives you 1000 megawatt day. I've just linearly multiplied this. Or if you say 10 kg of uranium-235 will give you 10,000 megawatt day. So 10 kg can be considered as 1% in a ton of fuel. So I can say that 1% of uranium-235 in uranium will give me 10,000 megawatt day per ton amount of energy. So this is the unit of burn up. This is the amount of energy extractable or amount of energy extracted per unit mass of the fuel. So 1% of uranium-235 in uranium will be giving, if it undergoes burn up completely, it will give 10,000 megawatt day per ton of energy. Other units of energy, similarly megawatt day per ton, you can also make it gigawatt day per ton. There is another unit which is called in terms of fuel depletion, which is atom percent. Suppose I start with 1 kg of uranium-235, and after some burn-up, I am ending up with, let us say, 95 kgs of uranium-235. So which means 5 kg of uranium-235 has burnt or depleted. So the atom percent can be calculated as 5% depletion. So this atom percent is another way of giving the fuel burn-up, the amount of fuel which has been used up to produce that particular energy. So that is called as atom percent. From irradiation point of view, we have another unit which is neutron per kilobarn. So you have this neutron, and sigma is nothing but your cross section, and sigma into phi is nothing but your reaction rate. So it can also be expressed in terms of neutron per kilobarns. I am giving you a small mathematics here just for you to understand what is the amount of energy which is being produced in a day. We already saw that 1.05 kg of uranium-235 gives you 1000 megawatt day. So the production of heat of 1 gigawatt requires about so much of fissile per day. So I wanted to tell you how much of uranium-235 is burnt. And let's take a simple reactor. I'll just come to that in a short while. So the fission rate or fissile consumption can be worked out. If you have P watts, which is being produced in a reactor, it will be 1.05 into 10 to the power of minus 9 P into kg per day. So the rate of consumption of the fissile can be also calculated in terms of the fission cross-section and absorption cross-section. I think you will understand it better with an example. In a PHWR, how much of uranium-235 is burned? So let us take a 220 megawatt PHWR, which will be giving 750 megawatt thermal. By the way, all these power which we are calculating is from the fission reaction rate. So it is called as a fission power. Out of these fission power, 95% is what is going to the coolant, or it is extractable as a thermal energy. So this 750 megawatt thermal is basically that amount of energy which has been given to the coolant to take to the secondary side and so on. And this is the conversion from the heat to the electricity, which is about 33%. You get 220 megawatt electric. So you work out the mathematics from the energy from point of view. You get 750 megawatts, 750 into 10 to the power of 6 multiplied by 24 hours in a day, and how many? 60 minutes and 60 seconds. So totally in a day, you will produce 6.48 into 10 to the power of 13 joules if a reactor is having this kind of a power. Therefore, 1 kg of uranium-235 gives you 80 terajoules. So therefore, in one day, PHWR will burn about 800 grams of uranium-235. This is simple mathematics. You can work out from the first principles also. This is another way of looking at it. If P is the operating power of the reactor and ER is, this is a general thing. Whether I had given a specific example, here I'm giving you a general formula for calculating the fuel burn-up or the reactor power or the fuel consumption. If ER is a recoverable energy from a single fission, in our case, it's around 200 MeV or so, then the fission rate is given by P into 10 to the power of 6 joules per second. This is not 106, it should be 10 to the power of 6. I'm sorry for this. I'll change this and just send it to you. There is something happens with respect to the powers when I convert to PowerPoint. So P into 10 to the power of 6 MeV into 24 into 3600 divided by the conversion for electron volts to joules. And then here you can see that it is 1 by ER, which is the recoverable energy. So many fissions per day would be there. And this can be simplified as 5.4 into 10 to the power of 23 into P by ER, fissions per day. So in order to find out in grams, what is the fuel that has been fissioned or consumed? So you can calculate 1 by uranium-235 is the main fissile nuclide. Then you can say that this comes out to be 5.4 into 10 to the power of 23 into P by ER into 1 by N235 grams per day. So you can take the Avogadro's number and calculate how much fissioning. It will come out to be the same, 800 grams or 788 grams or so on. So in general, if A is the atomic mass of the fissioning nucleus, the amount of fuel depletion in a day can be given as 0.895 P into A by ER grams per day. So this is the amount of depletion which is happening for a reactor with a power P and a fissioning nucleus, which is, let's say, uranium-235, and its recoverable energy, which is 200 MeV per fission. So this is how you can see what is happening to the reactor in a day, how much power is produced and how much fuel is getting consumed. I can just go for another 5 minutes because I just want to introduce this concept. So tomorrow I will go for basic reactors and so on. So far we have seen the steady state behavior of the neutron. I wanted to just give you a concept of the time dependent behavior so that you understand that in a transient situation, it is very important to take into account how the neutron population changes with respect to time. Let K be the neutron multiplication factor. The rate at which the neutron population increases is then given by K, which is equal to neutron population at time T plus L, some time T plus L, divided by a population at time T is equal to T. Or dN by dt is nothing but K minus 1 by L. This you can, if I expand this and take it to the left hand side and do that, I'll get rate of change of neutron population is nothing but K minus 1 by L. I integrate this equation, I get N into N is equal to N naught into E to the power of K minus 1 into T by L. So now this is what is our governing equation for the neutron population to increase with time. Now L is the mean generation time. So in 1 second, the neutron population will increase by K minus 1 by L. Okay. So in 1 second, the neutron population will increase by K minus 1 by L. So T by L can be seen as the number of generations. We said how many generations are there for the neutron population to increase. So T by L is nothing but a generation, and K minus 1 is seen as an excess multiplication factor. I'm giving you a small mathematics, small problem here. You can calculate the time required for the neutron population to double if K is equal to 1.003 and L is equal to 1 millisecond. You calculate this log of 2n by n naught is equal to 0.03 n, which is nothing but 231 generations, the neutron population will double. Or T is equal to 0.23 seconds for the neutron population to double. If L is 1 millisecond, then you can calculate T is equal to 0.23 seconds. So in 0.23 seconds, the neutron population will double. But this is so if the mean generation time, here I had talked to you, that is about 1 millisecond. This 1 millisecond will be manifested only when there are only prompt neutrons. But in a chain reactant system or a chain reacting volume, you have both prompt neutrons and delayed neutrons. So the mean generation time is going to be both L prompt and L delayed. Both have to be considered. And because of the presence of delayed neutrons, which are having about 55-second half-life, 23-second half-life, and so on, your mean generation time is actually not in the form like milliseconds. It is going to be greater, which is 0.1 seconds. So for the same example, the neutron population will double in 23 seconds and not in 0.23 seconds, which is a safe situation. So delayed neutrons basically help in controlling the chain reaction. So that is why I said both sustained and control both are important. So the delayed neutrons are, by their inherent properties, they are available to us to control the chain reaction and increase the mean generation time. Otherwise, my neutron population will increase in such a fast pace and will not be able to control. There are other concepts which says that the neutron lifetime basically depends upon the delayed neutron fraction. And there is an expression for that. I'm not going into all that. That will be a little more advanced for you kind of people. But basically, if somebody is interested, you can see cluster. I would only just introduce the concept of E folding time. We already derived an expression for n by n naught is equal to e to the power of k minus 1 by t into t by L. And if t is equal to 1 by k minus 1, the neutron population will increase by e times. So if t is equal to 1 by k minus L by k minus 1, then your neutron population will be increasing by e times. So far we were considering in the example how the neutron population doubles. But actually this e folding time is very important because the quantity L by k minus 1 is called the reactor period. The reactor period is a period or the time over which the neutron population increases by a factor of e times, this is the way in which the exponential function, so it increases by e, or this is called as an e folding time. So the reactor period is very, very important parameter, and this is the one which is being monitored in a reactor. So in the control room, you will just directly get the reactor period, and from the reactor period, we know whether the chain reaction is increasing or decreasing, or thereby how the control has to be initiated. In the presence of delayed neutron, the reactor period will be large. So about the time dependent behavior, only this much I'm going to say, not much, but I just to make you understand that there could be situations in the reactor which is departure from criticality, or the chain reacting system is not balanced, and then your neutron population could increase. So in summary, for this lecture, we have derived the basic neutron balance equation. We saw the steady state. For the steady state conditions, how is the neutron balance equation? And then we also said that phi as a function of both space and energy have to be determined. Phi as a function of r we have determined with respect to the wave equation which we formulated. And energy treatment also we saw something like what is the fast group and the thermal group. Then I have introduced the concept of buckling, the geometric and material buckling, the conditions for criticality, how the material properties are have to be equated to the geometrical properties in order to get the criticality conditions, and an understanding of non-leakage probability both from the material and geometrical buckling point of view. And we also derived an expression for the critical radius. We saw the bare homogeneous reactor. I have given you the flux profile in a typical cylindrical reactor. And I have given you the difference between the diffusion length and the migration length. We also give an expression for calculating the neutronic power or the fission power of the reactor. And I have also told you that how the thermal power is different from the neutronic power. And some definition of burn-up and fuel depletion. And we did a small mathematics of what is a fuel depletion and typical natural uranium fuel PHWR. And also the time-dependent behavior of the neutron population and what is meant by reactor period. So this is what I wanted to tell you today. I hope it was again a little loaded lecture probably, but I hope you have understood some things.